Next, I want to solve a problem of type 1. This is the problem statement shown on the slide. ABC points A, B and C. They are points on a massless rod. I am calling that as RB1. There is a disc attached at the end of this massless rod. C is the center of mass of that disc. I have marked here A and B, radians per second. A is the angular velocity of the rod ABC with respect to this I frame, whereas B is the angular velocity of the disc with respect to what? It would be with respect to the rod ABC itself. And they are constants. The scalar A and scalar B, they do not change with time. Okay. Now I have written a comment here to help you visualize. Arm ABC lies in a vertical plane. Arm ABC lies entirely in a vertical plane. And that vertical plane in which ABC lies is of course moving, rotating with angular velocity A as marked. The disc, which is RB2, is also lying in the plane of ABC and it is rotating with respect to RB1 with angular velocity B. I hope you are able to visualize. There are some dimensions given. This is 450 mm, this is 150 mm, this is 225 mm. What are we supposed to find? Reaction force system being exerted by the support on RB2 at point C. C is a pin joint. C is a pin joint. Also, numerical values of A, B and C are also given, which we will need eventually to get the numbers. Mass of the disc is 4 kg. But more than numbers, this problem needs really good insight and clarity about the procedure of getting the solution. One of the more difficult problems that you will come across. If you are able to understand this, you will be able to solve many other problems. Okay. We will follow similar steps that we followed to solve the type 2 problem, the previous problem. First step is to judge. Judge what? Whether it's a type 1 or type 2 problem. Judge based on the given information, not because I have written that on the heading itself. That's part of the organization of my slide. But if this problem comes to you in real life or on an exam, that heading type 1 will not be there. You have to judge type 1 or type 2. The criterion to judge that is look at omega mi. It can always be written as omega times E hat, but whether that E hat is stationary with respect to I or not. In this question, M is what? M is RB2. Okay, so omega 2I will be what? Omega 1I plus omega 21I, omega 21 and then omega 1I. What is omega 21? That is, okay, B times I have shown a coordinate system. It is along E3 plus omega 1I will be, according to the coordinate system shown, it will be A times E2. So omega 2I is along some direction E. You can write that as something times E hat. But is that E hat stationary with respect to the inertial frame or not? It is not, because even though this may not be changing, this is changing with respect to I. Changes. Okay, and thus dE dt I doesn't seem to be stationary. Okay, and that is why it is a type 1 problem. dE1 dt I does not seem to be 0. I need only this much conclusion. Does not seem to be 0, and thus I will conclude it is a type 1 problem. Move to step number 2. What do we have to find? Identify your working coordinate system. If you go back to this slide, the very first slide of the lecture today, this one. A must be part of the RB. You should choose the working coordinate system to be this, such that these three axes are the P axis of RB at point A. Choose A to be a valid point for MESA version 1. These are my suggestions for type 1 problems. So following B and C, I am going to choose my coordinate system to be this. The origin of my working coordinate system is the center of mass of the disk. Is it a point fixed on the body? Indeed it is. Is it a valid point for MESA? Indeed it is. Center of mass is always a valid point for MESA. Okay, and the three axes, what I have shown here, are all fixed to RB. Note x1 E1, x2 E2, x3 E3 fixed to RB. Are x1 E1, x2 E2 P axis? Are these P axis? Yes, they are. It's a body of revolution. x1 E1 and x2 E2 is always a principal axis. x1 E1, x2 E2 are principal axis, and the axis perpendicular to the plane of the disk is also a principal axis. So this coordinate system, what I have drawn in black color on this figure, satisfies everything that I wanted to have before I can start solving a type 1 problem. Have a look at it again, going to slide number 1. Type 1 problem, A is fixed to RB. There I have chosen that point to be C. What is A here is C there. C is center of mass, indeed fixed to RB. C, x1 E1, x2 E2, x3 E3 are chosen such that these three are the P axis. Indeed they are for that thin disk. Choose A, which there is C, to be a valid point. Since I have chosen center of mass to be the point origin of the coordinate system, it is indeed a valid point, no doubt about it. Everything satisfied. So this is a good choice of coordinate system. Let's move forward. Step 3. Draw a free body diagram. Free body diagram of what? Free body diagram of the disk RB2. That's my system. Okay. I'm going to draw the free body diagram. Something like this. Okay. Right now, the coordinate axes are oriented in this way. What are the forces acting? mg acting at the center of mass of the disk. What other forces? What other forces? The other forces would be the reaction force system. Now let's represent that reaction force system by a single force F vector accompanied by a moment. Let me put this as CR. And let's call this as FR. Putting the general vector form. I will use the shown coordinate system as my working coordinate system, but let me just write this right now as FR and CR vectors. One force and one torque. Okay. Step 4. Euler's first axiom. Euler's first axiom tells me the net force must be equal to mass times acceleration of the center of mass with respect to frame I. What is F net? F net is the shown force Fr minus mg times E2 at this instant. I am talking only about this instant. At this instant I am letting x2 E2 be vertical. At the next instant x2 E2 may not remain vertical. Why? Because x2 E2 is tied to the RB2. Okay. At next instant mg may not be along minus E2. After all, E2 is part of RB2. So as RB2 rotates, E2 will rotate and mg may not be along E2. I don't worry about it. I am worried only about this instant. At this instant, this is true. Okay, so this is the left hand side. Right hand side is M ACI. What is ACI? ACI. How do we write ACI? Again, you can write ACI directly in a more direct way, or you can use the concept of IF as RB1 and IP as point A. A is fixed to IF. A is here. This is it. So ACI can be written in this manner. There will be of course two more terms, omega 1I cross VC1 plus AC1, but C is a point fixed in RB1 also, and that is why this will cancel out. We are left with this term. What is omega 1I? What is omega 1I? My claim is that, what is omega dot 1I? By definition, omega dot 1I is this. Always with respect to I, right? Omega 1I is always in the vertically up direction. Also, magnitude of I, magnitude of omega 1I, which is what? Which is given to be A, is constant, given. Alright. Thus, as seen by observer fixed to ground, omega 1I never changes. Its direction is always upwards, magnitude is always A. For a vector to change, at least its magnitude changes, or its direction has to change as observed from the inertial frame. But I have acknowledged that neither the direction nor the magnitude changes, and thus this vector, rate of change of vector is 0, or omega 1I is 0. Okay, so this I will say is a known quantity. Given the geometry, RCA can also be written. RCA can be expressed using the numbers given. It turns out to be 0.045 times E1 at this instant plus 0.225 times E2. Meters at this instant. I'm using the working coordinate system. This 0.45 along E1, which is coming from here, 0.225 along E2, which is coming from here. So RCA is a known vector too. RC is a known vector. Omega 1I is of course known. I should have actually processed this before omega 1 dot I. Omega 1I is what? A times E hat, where E hat is vertically upwards vector, and that is actually at this instant nothing but A times E3. A times E2 actually. A times A at this instant. Right? After all, at this instant, E2 is vertical. E2 is vertical at this instant, and that's why I can write at this instant omega 1I is A times E2. I should mark this as a known quantity. This is a known quantity. AAI is also a known quantity. It is 0 actually. A is a point fixed in I. Alright. So if you take the contributions from these two, turns out that ACI is known. Okay. I'll write the numbers here for your verification later on. ACI according to me turns out to be minus 11.25 meters per second square along E1. Okay, so actually this doesn't count. ACI is minus 11.25 meters per second square. So going back to the Euler's first axiom, I have here FR minus mg2 is MACI. FR minus mg2 is mass times minus 11.25 meters per second square. Let's call it equation number 1 along E1. Have we found FR? Looks like we have already found FR. This is 11.25 along E1 plus mg times E2. Okay. Final answer I am leaving with you for your verification. Turns out to be this much. Verify. Newtons. What did they ask us to find? They asked us to find the reaction force system at C. The reaction force system at C involved a force which I have found. This has been found. Now I need to find CR. Let's try to find CR. Okay. Finding CR means going to the next step, which is step number 5, using Euler's second axiom. Step 5. Apply Euler's or MESA, and the version will be V1 because it is a type 1 problem. Okay. Equations are as before. One more time I will have to write. Note that in the original MESA V1 equation, I was using point A. A appears there. A was a valid point. In this problem, I have chosen A equals C. That A equals C, center of mass of RB2. And thus, you see MC1, MC2, MC3, and you see all the inertia components being written about point C. C is relevant here. Alright. What is MC? And what are MC1, MC2, MC3? They must be the scalar components of this vector. Where this is the net moment due to the external force system acting on RB2 about point C. Let's go back to the FBD to find what MC would be in this problem. FBD. There is a force mg acting, but that passes through C, right through C. Passes through C. It will not count. No contribution to MC. Fr is a force acting again at C. Passes through C. No contribution to MC. You are left only with one non-zero contribution, and that is the CR itself. CR is the net moment. CR is the net moment of the external system about point C. That's all. And that is the unknown. So I'm going to write, we are going to get an equation for CR directly. MC is nothing but CR. Now if you wish, you can write CR as CRE1, CRE2 and CRE3, CR1E1, CR2E2, CR3E3. If you want, you can write. But then if I am able to get everything on the right hand side and put coefficients E1, E2, E3, I will get CR directly anyway. Either way, the left hand side is going to be in terms of the quantity that I am looking for. So that is okay. I don't need to do any further processing on the left hand side of these three equations. Okay, we really have to work on the right hand side. Now right hand side has some inertia components, and it has some velocity, angular velocity components, and it has some angular acceleration components. I have said this 3-4 times earlier also. The learning here is really not remembering the formula, but being able to understand what these symbols mean. IC11, IC22, IC33, I think it is quite clear. It is a thin disk, so we should be able to identify those readily. There are three inertia components appearing here. Given the coordinate system, IC11, look at the working coordinate system, black colored working coordinate system. IC11 is mr square by 4, IC22 is mr square by 4, IC33 is mr square by 2. I derived this in lecture 27-28, thin disk. Okay, going back to the previous slide, I know these things. I know these things. What are the next unknown things? These. What are those things? Those are the scalar components of the angular velocity of what with respect to what. That is important to understand. Omega mi, or rather I should directly write as omega 2i, because that is the body of interest. You should be able to write this as this. But these are right now just symbols. What exactly are they? To know what exactly are they, you actually have to look back at this figure and understand that omega 2i is actually omega 21 plus omega 1i. Omega 2i is omega 21. This is a very important step. Having clarity about what I am doing right now is very important to solve similar, seemingly difficult problems. Omega 21 at this instant is what? If you look at this figure, RB2 and 1 I have marked. What is omega to 1? It is going to be at this instant B times C3. And what is omega 1i at this instant? It's A times E2 at this instant. And I am worried only about this instant. I am concerned only about what is. I mean, this problem is being solved at this shown instant only. Okay. So these are known quantities. This is known. This is known. You see, it's given beta 15 radians per second, A is 5 radians per second, E2, E3 is a working coordinate system. I would deem omega 2i to be known. How does it help me get these omega 1, omega 2, omega 3? All you have to do is to write this as 0 times E1, A times E2, and B times E3. And thus, omega 1 is 0, omega 2 is A, and omega 3 is B. These are the values that must go back in this side of the equation. Alright, so I have taken care of all these things, this product taken care of. What is the next unknown here? Omega 1 dot, omega 2 dot, and omega 3 dot. How do I get that? I explained it during my lecture. While I was deriving MESA V2, I said that to be able to get omega 1 dot, omega 2 dot, and omega 3 dot, you should first write your omega mi, which in this case is 2i, in this form. You should be able to write. Should be able to write it in this form. Whatever is this will be omega 1 dot, whatever is this omega 2 dot, whatever is this, it will be omega 3 dot. Fine. So let's find omega dot 2i. And this is something I've done many times before during the kinematics part of the course. I am going to write this as omega 21 dot, omega 1i dot, omega 1i cross omega 21. Now pay attention to this. Omega dot 2i, omega dot 21 is 0. Why? Because with respect to 1, omega 21 neither changes its direction nor its magnitude. Needs a little bit of visualization. However, we have done this exercise earlier also. I have explained this concept earlier while solving kinematics problems. Okay. And omega 1i will be 0 because omega 1i dot will be 0 because with respect to I, omega 1i neither changes its direction nor its magnitude. I will take 2 more minutes and complete this question. Okay, so this is 0, this becomes a known quantity, this is 0, this is also unknown, this is also a known quantity, we found it just here, right? Omega 1i is AE2, BE3. Take the cross product of AE2 and BE3, it will turn out to be omega 2i dot turns out to be simply ABE1, nothing along E2, nothing along E3, and thus my conclusion is that omega 1 dot should be AB, omega 2 dot should be 0, omega 3 dot should also be 0. Going back where? With known. Okay. If you look at this set of equations, MC1, MC2, MC3, right hand side is completely known and left hand side is just CR1, CR2, CR3, which you have to find. And thus I'm going to write the final solution here and leave it for you to verify and get comfortable with all these ideas. CR will turn out to be MR square by 2 ABE1. That is the final answer. Solve and verify. This is the final answer. Okay. CR, FR known. Okay. So please solve this problem on your own. Make sure you understand all the steps. I'm telling you, your performance on the major exam critically depends on your understanding of this problem. With these words, I stop. We will meet tomorrow again at 4.